we're now going to go back and look at gravitational potential energy. We're going to start by just dusting off the cobwebs for what we've already studied with potential energy, because we need the basic structure for how potential energy is defined to apply it to our new equation for the force due to gravity, and the one on r squared dependence, the inverse square law. Let's go see how we applied the basic definitions for the constant acceleration to get us kind of back thinking in this way. The basic definition for potential energy, regardless of the force function you're using, is given by the change in potential energy, right? We need two potential energy values. Only the change in potential energy has physical meaning, and by definition, delta U is negative the work done by the conservative force. In our case, we're focusing on gravity. Now, in Chapter 8, I have just a repeat of what we talked about there. We looked at lifting an object from the surface of the Earth, and of course gravity does not shut off when you do that, so gravity is still there. So when we calculate the work done by gravity, we have the force due to gravity, mg, we have delta y is up, we get our cosine of 180, so we get a purple negative in here, negative mg delta y. Hopefully this is beginning to ring some bells for us, remembering that calculation. We're going to go back and plug in the work done by gravity into our delta U. By definition is negative the work done. We get our purple negative here from our negative here. We have the negative that's in our definition still there, so we get those two negatives give us a positive for the delta U calculation. Now, of course, the change in potential energy, delta U, can be negative, right? When y final is less than y initial, you're losing potential energy as you go downward, and we picked off one of these equations, mgy, as our potential energy function equation. So we're going to apply this same type of analysis, the same basic structure to getting a potential energy function, to our law for universal gravitation. So let's do that. Now this derivation is a little bit tricky, so you're not going to be responsible for memorizing the derivation. However, I want you to see mathematically where it comes from, because the derivation of our equation here for potential energy is going to result in an equation that we use very often, and our comfort level with it just simply needs to be there. Now, in terms of starting this derivation, we are going to start, as it says here, by looking at the work done by gravity as we bring an object in from infinity. Now, we'll see why in a moment that makes sense. In the case for universal gravitation, our gravitational force is our inverse square equation that Newton gave us. So that is going to be inward. Our displacement in our work calculation is also going to be inward. So when we do our dot product, we now get a cosine of 0. Now, it is important that we look at our positions initially and finally, and make note that our final position is not going to be at the surface of the Earth. Our final position will be at an intermediate position where we're leaving it as a variable r. We're just letting r final equal any variable r in from infinity. So here I have again the work equation with the dot product still in there. So the dot product is here. So as I said above, we get our ds is radially inward, our gravitational force is radially inward, we get cosine of 0. So when we take the dot product, we would get magnitude of the first, magnitude of the second, cosine of the angle between the two. So everything there would be positive. We would get positive. We would get, if we put in ds, a positive ds here, and everything would be positive. The trick to me to remember how to get this derivation correct, so please make sure you get this in your notes, is we have to replace the general displacement variable ds with the polar coordinate negative dr to be consistent with the r squared in Newton's law for universal gravitation. So that negative introduces this. I'm going to make it black, another black negative here. Well, now our derivation is in place. So our limits of integration we stated above. Final, initial. We have a polynomial function, integral r to the minus 2, integrate, increase. But look, we get another negative in down here. So I'm going to add that purple negative here. So I'm going to make that one purple. I'm going to leave the black one above black. So when we calculate our work done by gravity, we had our initial position. Our initial r was r equals infinity, so we lose the one term. The work done by gravity is going to be positive. Capital G, mass of Earth, little m over r. We are going to, again, use our mathematical structure for change in potential energy is negative the work done by the conservative force. Change in potential energy is always, right, final minus initial. And we are going to reference now. So this is arbitrary. We don't have to set this equal to 0. But we are going to set it equal to 0 to give us a very compact equation for the potential energy function. And if you look at the function we get, it makes sense because when little r equals infinity, we get the 0 that our reference gives us. So again, I know there's a lot going on in terms of tracking the negatives down, but hopefully we understand enough about potential energy, the basic concept of change in potential energy equals negative work done, and our math is to the point where we can understand this derivation. So please do get this page completely annotated into your notes. There certainly is nothing unfair here in terms of asking you on the AP test, but it is not a derivation that has been asked, and we will not have to just memorize this derivation for our quiz or tests as well. So we will move on with a deeper look at the potential energy function, and that we will be responsible for.